What's up guys? So today we'll be covering model mechanics for tree-based methods. Just a quick preface before we start this section. Certain terminology we'll be using interchangeably throughout this course. So what that means is that some of the mathematical objects that we'll be referring to carry one set of names from the world of machine learning and another set of names from the world of statistics. Okay, so the terms that will pop up quite often today are those of features and feature space. That's from the world of machine learning, where we actually mean predictors and predictor space from the world of statistics. Cool, so let's kick off with a data set. Okay, so I've given you a simulated data set, and what you can do is you can call this data set into R and print the tabulated data, and then what you'll see is that I've given you two covariates, so two continuous valued predictors or features, and a single response taking on values 0 or 1. Okay, and then I give you a simple task. Okay, all I want you to do is, given this data, I want you to predict the response. Okay, so how would you go about doing this? Well, so first thing you'll do is you'll recognize this as a supervised learning problem of the classification type. Supervised because we have an example of the response, and classification because the response takes on one of two values. Okay. Then what you'll do is, based on your knowledge of generalized linear models, you'll probably suggest that a good way to model this data in order to construct a prediction is to use logistic regression. Okay, and indeed you will be right. Okay, so how does logistic regression work again? Okay, so what we do is we model the response as coming from an appropriate distribution. In this case, it'll be Bernoulli. Why? Because the response takes on one of two values. And then what we'll do is we'll subsume the linear component under the assumption that the predictors are actually useful for predicting response within the parameter of that distribution. Okay, so that'll be that pi I, which denotes the success probability in the Bernoulli distribution. Okay, and we'll obviously require a link function in order to marry the linear component to the parameter of that distribution. Okay, now, given the data, what you'll do is you'll take this model, you'll pass it through the iterative weighted least squares algorithm, which you should be familiar with by now, and that'll give you some parameter estimates for the linear component of your model. Okay, so in order to construct a prediction, what you'll do is you'll plug those estimated parameters into the linear component, pass it via the inverse of the link function in order to estimate pi I, which is effectively your predicted probability of the outcome y equals 1. Okay, and in that way you can construct predictions. Okay, so what you'll do is, for any particular predictor that I give you, if I were to ask you to predict the corresponding response, you'd plug that into the linear component, get the probability out, and you'll decide based on that probability whether to classify an observation as 1 or 0. Okay, so a simple decision rule that we can apply is to say that whenever that probability is above, say, 0.5, we'll classify as 1. If it's below, we'll classify as 0. Okay, and in that way you can actually give me predictions. Right, so now my question to you is, well, what is the model actually doing? And what is the relationship between predictors and the response? Okay, so in order to see this, recall that the linear component effectively defines the equation of a plane in the feature space. Okay, and that plane is then passed through the inverse of the link function to give you a sort of sigmoidal surface or a probability surface, which is essentially each point on that surface is a prediction of the corresponding response at that coordinate in the feature space. Okay, and remember our decision rule says that whenever that probability is above 0.5, we'll classify as 1. When it's below 0.5, we'll classify as 0. Okay, so if you think of that probability surface as your predictions, then you can think of the decision rule as another plane which passes through that surface. Then the intersection between those surfaces essentially defines a linear decision bound in the feature space, which then gives you your predictions. Okay, so once you have that linear decision bound, what that tells you to do is go in look in the feature space. All the coordinates to one side of this line you classify as 1, and all the coordinates to the other side of this line you classify as 0. Okay, so to answer the question of what the model is doing, well, the model is simply partitioning the feature space into two subsets each associated with different outcomes of the response. So you've answered both my questions. Okay, you can give me predictions for the data set using a logistic regression model. I asked you what the model is doing. It gives you a linear decision bound. And now I ask you, well, what if the data is nonlinear? Okay, indeed, the way I constructed this example was to make the data nonlinear. Okay, so I'm cheating a bit. I'm telling you that it's nonlinear. But then, does it suffice to have a linear decision bound? Okay, so we plot the data, we plot the bound, we see that, okay, it sort of makes sense, but maybe there's some shape to the data. Okay, so if you look at the plot, you'll see that all the tags which are 1 show up in the top right-hand corner of our feature space. Okay, so how do we construct that feature using a logistic regression model? Okay, so one way we could do this is by including interaction terms in the linear component of our logistic regression model. Okay, now what this will do is this will in effect create a nonlinear decision bound using a linear model in the feature space. Okay, but in effect, it's still doing the exact same thing, right? It's still partitioning the feature space into two subsets associated with the possible outcomes of the response. Cool. So in this case, that works pretty well. But what if the data that I've given you was really highly nonlinear? Okay, so what if it was something like a picture of a face, or our data would presumably be many pictures of faces, or something like that. Could you use a linear model to classify those as being of one response or another? Okay, using a simple linear model. Okay, and this comes back to the question I raised earlier. Can a statistician always come up with an appropriate mathematical expression linking the predictors and the response? Okay, and the answer is obviously no. Okay, but is there still something here that we can use? And the answer is yes. Okay, and indeed, this is the departure point for the analysis of tree-based methods, the idea of partitioning the feature space. So the premise behind tree-based methods is to mechanically partition the feature space. So this is achieved by systematically splitting the feature space along its dimensions in order to create regions in the feature space where we effectively conduct local regressions. Okay, so to demonstrate how this works, what I'm going to do is I'm going to walk you through the underlying algorithm using the simplest possible scenario. Okay, so I give you a sample of n observations on a single feature and a real valued response. Okay, so you should recognize this as a univariate supervised learning problem of the regression type. Okay, what we'll do is I will formulate the steps of the algorithm using only the notion of partitioning with the aim to improve prediction accuracy. Okay, cool. So, in the absence of any assumptions about the relationship between the feature and the response, if I were to ask you to predict the outcome of a new observation, a plausible strategy would be to simply take the mean of the sample responses. Okay, cool. Then, if I were to ask you to judge whether this is a good prediction or not, you could again allude to the sample data and compare how well this prediction fares for existing observations. And the way we do this is by simply checking how far is this prediction from the observed responses that we have. Okay, so you calculate those distances, and then what you can do is you can take this a step further and you can summarize it empirically in a single number by simply adding up those distances. Okay, and you should recognize this as the so-called residual sum of squares. Right, now the question is, can we improve on these predictions by invoking only the notion of partitioning? Okay, well, presumably there's some information in the predictor which may be useful for predicting the response. Okay, so let's plot the response as a function of the predictors and see. Okay, and indeed, comparing the predictions to the responses, we see that for lower values of the feature, we are consistently predicting too high, and then for high values of the feature or predictor, we are consistently predicting too low. Okay, so invoking the notion of partitioning, perhaps we could partition the feature space into two regions, okay, isolating the responses from those regions and reformulate our predictions. So by visual inspection, we could maybe guess that a good place to do this would be around the point where we stop over predicting and start under predicting. Okay, so indeed, if we split up the data into two subsets and do that, what we'll see is that our predictions improve substantially. Okay, and the way that we know this is we check, well, how far are predictions for each one of those regions from the sample observations in those regions. Okay, and again, if we were to summarize that in a single number, what we'll see is that we'll note a reduction in the residual sum of squares. Cool, so we've successfully invoked the partitioning principle in order to improve our prediction accuracy. But we've done so by visual inspection, right? And this hardly constitutes an advanced machine learning strategy. Indeed, it will only be in rare cases of the applications that we have in mind that visual inspection would be tractable in the first place. Okay, so what we need to do is we need to make this procedure more mechanical. Okay, so for these purposes, what we can do is we can conduct a numerical search along the feature dimension for the split point which best partitions the data. Okay, and best here will be informed by prediction accuracy. So in this case, what that means is finding a point along the feature dimension at which the residual sum of squares is reduced the most. Okay, so we conduct a simple numerical line search, and in that way we find the split point numerically. Cool, so we now have mechanical means of partitioning the feature space, and thus concludes the first major element of our learning algorithm. That is the so-called partitioning step. Okay, now to summarize, this element provides us with a split point in the feature space, defining a simple decision rule. This decision rule partitions the feature space into two regions from which we then construct our predictions. Okay, but again, are we satisfied in our pursuit of prediction accuracy? Can we perhaps improve on this further? Okay, now noting that after this first split, we are essentially left with two subsets of the data, which we can then treat as separate prediction problems. There's nothing to stop us from applying the partitioning step to each of these subsets, right? So in doing so, we observe that for the first subset of region 1, there is no split point which produces a marked improvement in prediction accuracy. Whilst on the second region, if we apply the partitioning step, we find another split point which actually improves our prediction accuracy. So as such, we decide to partition on the second subset of the feature space and then leave the first region unchanged. Okay, since there doesn't seem to be any information in the predictor which actually helps us improve our predictions in that subset of the feature space. Okay, now note here that after the second iteration of the partitioning step, we've produced two nested decision rules. Okay, so the decisions themselves are binary, but the nesting allows observations to be sorted into three distinct regions. Okay, and if we need to, we can continue partitioning recursively, so i.e. for many more iterations on those subsets that we've defined. And indeed, it is this nesting which allows the tree-based methods to capture complex and nonlinear association structures between subsets of the feature space and the response. Okay, now after many iterations of the partitioning algorithm, it may be difficult to keep track of the decision rules and the association structure it defines. So a useful way to summarize these nested decision rules graphically is to simply plot the decision tree. Okay, so what this is this summarizes the decision rules in a hierarchy, where the hierarchy gives the sequence in which to apply the decision rules. Okay, so the tree plot starts out an initial root node corresponding to observed region of the feature space. The first split is then applied and indicated on the tree, and then two new branches are drawn with nodes corresponding to the regions defined by the first split. Each of these nodes may then be further split from new branch to form new branches, or left as as is if no new partition is found. Okay, so in our present example, we've applied 2 iterations resulting in 2 nested decision rules, the second occurring on the right split of the first. So our tree thus terminates in 3 so-called leaf nodes, okay, to which we tag the predictions constructed from the corresponding regions. And this concludes the second major element of our algorithm, the recursive application of the partitioning step. Okay, so in combination, these 2 elements define a systematic procedure which iteratively defines a set of nested decision rules with the sole objective of predicting the response. So at each iteration, our predictions are also expected to improve. Okay. As such, this process constitutes a machine learning algorithm. So that is a mechanical set of instructions which takes observations, learns to associate coordinates in the feature space with the response, and produces accurate predictions. So as with all machine learning algorithms, we cannot blindly pursue accuracy and apply partitioning for error. We'll have to invoke some stopping criteria for our algorithm. And indeed, we've already applied this so-called stopping criteria to on the second iteration of our example problem. Now, we can also define a number of other stopping criteria, but we'll probably run into these during the lab sessions. Now, note that though these can be considered minor elements of our learning algorithm, they do play an important role in the behavior of the algorithm and consequently its ability to learn association structures. But one really does need to sort of analyze some real world data sets to get a feel of what the effect of those parameters are on the analysis. Right, so before we conclude this section, there are 2 more important aspects of the model mechanics that we need to discuss. The first is the objective function when we apply recursive partitioning to a classification task. And the second is partitioning when there is more than one feature or predictor. Okay, so for these purposes, what we'll do is we'll revisit the dummy classification problem from earlier. And recall that we had 2 real valued features on a single categorical response, and the response was encoded as 0s and 1s. Right, now, if we want to apply the recursive binary partitioning procedure to this data, the first issue we are presented with is what objective to pursue, right? So in the regression setting, this was easy because, well, we could simply check how far our predictions are from the observed example responses to measure how well our algorithm is doing at any point along the procedure, right? Now, for a classification task, well, how do we do this? We essentially need to define first how we construct predictions, and then sort of redefine our notion of distance when we measure the distance between our predictions and responses. Okay, cool. So, how do we construct predictions? Well, recalling that the algorithm defines the regions in the feature space where we conduct local regressions, we can construct predictions using an empirical estimate of the probability of the response outcome, right? So that is, our prediction for any given region is simply the relative frequency of the response in that region. Okay, so for our dummy classification example, on the first split, what we do is we look at each region and then we estimate the probability of the outcome y equals 1, simply as the number of responses we observe to be 1 in each region divided by the number of observations in those regions. Okay, and the same sort of argument applies to the subsequent nested partitions. Right, cool, simple enough. Now, how do we compare how far these predictions are from the observed responses? Okay, what does it even mean to measure the distance between a predicted probability and a discrete response? Okay, now for these purposes, what we can do is we can essentially redefine our objective function in terms of the so-called impurity measures, which contrast the predicted and observed responses. Indeed, there are a number of measures which can be useful for these purposes, and the source material for this course lists three popular measures for measuring impurity. Okay, so the first is the misclassification rate, The second is the so-called Gini index. And then finally we have the Shannon entropy. Okay, and this is not to be confused with cross entropy. We'll cover cross entropy later when we get to neural networks. But there's an important distinction which I'll cover there. Okay. Now note that though these measures differ in their sensitivity to the prediction inputs, which may affect how the algorithm constructs partitions, more on this later, they all do essentially the same thing, right? As the name suggests, they essentially measure how pure a node is by returning a low score when the predictions are mostly of a single type. So in this case 0 or 1, and high scores when there is one or more, or when there's more or less the same number of each type of the response. Okay. Now, since the measures are constructed purely with reference to the predicted responses, when we define the objective function in this way, and we aim to minimize this objective function at each iteration of the partitioning step, we are effectively pursuing the most decisive set of decision rules, which identify a clear association structure. Cool, so that takes care of the objective function. Next, we need to decide what to do with multiple features, right? So for these purposes, we modify the instruction set of our learning algorithm as follows. Okay, at each iteration of the partitioning step, search for the split point along each of the dimensions of the feature space, but only apply the decision rule that produces the greatest reduction in the objective function. Okay, so in the case of our dummy classification data, we see that at the first iteration, the splits along both of the feature dimensions would result in significant reductions in the aggregate impurity, right? But the greatest reduction is given by covariate 1, okay, or conducting a split along the dimension of covariate 1. Now, we thus apply the decision rule corresponding to the split point at the minimum of the objective function in the first feature dimension. Okay, then at the next iteration, we apply the same procedure to the subsets defined by the split point along the first feature dimension, and we subsequently find another split in the second region, but this time along the second feature dimension. Okay, now, since we have a two-dimensional feature space, these splits define rectangular regions in the feature space associated with various outcomes of the response. Okay, and indeed, we see that the algorithm identifies a rectangular region to the top right of the feature space, which is associated with the outcome 1, and then for all of the other regions it identified, it associates the outcome 0. Now, this is similar to what we saw with the logistic regression, right? Only this time, the algorithm identified the appropriate structure without the aid of structural intervention by you as the statistician. Okay, so I hope it now becomes immediately obvious why these models are so useful and so powerful in complex supervised learning problems. Okay. Now, just before we conclude, let's revisit the decision tree plot when we have multiple features and or categorical responses. Okay, so first we note that the structure of the tree has not changed fundamentally from our one-dimensional regression example we had before. The only modification in addressing multiple features is that the labels for the decision rules simply indicate which variable the corresponding rule is applied to, and we move through the hierarchy as usual. Okay. Secondly, for the leaf nodes of a classification tree, the predictions are simply given as the class labels corresponding to the predicted probability for each terminating node. Though it would probably be useful to plot the probabilities as well, but that's just a matter of tweaking the software. Okay, cool, and that concludes model mechanics section for the tree-based methods. In the lab sections that follow, we'll explore the ideas we covered in today's lecture using some real-world data and check out some R code for fitting tree-based models. And then in the next lecture, what we'll do is we'll move on to managing complexity, where we'll see that there's more to machine learning than torturing a particular realization of the data generating process with your favorite learning algorithm.